1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Okay. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're ready to go. Hey, Greg. Welcome. Very happy that you could all make it. This is a really big day for us in the STEM Pack project. We're going to hear about the work that students who were from Union County College spent the summer, most of the summer anyway, with professors from Kean doing research in mathematics and chemistry. And most everybody that I talked to had a pretty good time with this. There were some little bumps in the road that we had to iron out in the beginning, but I think by the end of the time period, things went very well. We have a number of people from the chemistry department, some people from the math department. We have the associate dean of the College of Natural Applied and Health Sciences, Dr. Brian Teasdale, Dr. Feng Qi from our, I know this is not the name of the program, it's what everybody calls it, Sustainability Program. SES, right? Yeah, okay, great. I'm not going to try to remember everybody else's name because I have holes in my brain. So I apologize ahead of time for that. But I'm not going to waste any more time with my babbling because we have much more intelligent people to talk about their work. And our first person is going to be Michael LaCourte. And Michael worked with Matt, right? Matt Mongelli.
Thank you. Good afternoon, everybody. My name is Michael LaCourte. I had the pleasure of working with Dr. Mongelli this summer on asymmetric ruthenium complex interactions with DNA. But before I get into the details of all this, I just wanted to give you a little background info on myself. I'm a biology and education major at Kean University here. I just graduated from UCC back in May, and I'm looking at becoming a teacher. I want to get certified to teach both biology and chemistry. Also, before I really dive into this, I want to talk about just the overall experience of this internship. What I wanted to get out of this was to get experience that I could bring into a classroom, be able to draw on the experience here and take real-world knowledge of scientific research into a classroom to motivate and then inspire students. And I got exactly that. It was absolutely a wonderful experience. A major takeaway for me was about remaining unbiased and open-minded as you complete any type of scientific research. The reason I say that is because of the results that we achieved were not in line with expectations. And I think it's very important that you keep that in mind as you move forward with any type of research, that sometimes the answers that you get might not be the answers that you want, but they're still the answers. Additionally, as a transfer student from UCC to Kean, this was an excellent opportunity for me to meet the wonderful staff here at Kean, and I think it was a great open door to go through as I make this transition. So, just a couple quick references. I didn't have to put this in here, but I felt obligated because there was information that I used straight out of several research papers. This experiment, it was designed to exploit the light-absorbing properties of ruthenium metal complexes. Those are the two. I'm not going to try and call those out for you. They're going to be referred to as BPM and BPY. That's the easiest way to keep them straight. You're probably asking, what is that? And this is what we have here. These are the two molecules. So in the center, we have ruthenium molecules and the ligands around the outside. We used PUC18 DNA, which has two forms. There's the supercoiled and the compact forms. Both forms are very, very easily distinguishable when completing gel electrophoresis, and I'm going to show you that as we get a little further into the presentation. DNA that has experienced binding with the metal complex shows a change in band intensity on the gels. So as I said, previous research indicates that the ruthenium-based organometallic compounds have the potential to demonstrate photocleavage of DNA molecules. It's due to a strong metal to ligand charge transfer property between the ruthenium atom and the ligand components. And again, you're probably asking, what does he mean? So here, what we have is we're talking about the ruthenium atom that enters an excited state. This is typically due to exposure to visible light spectrum. And as the photon comes in, ruthenium enters an excited state. Electrons bump off to the side of the molecule. That is what results in this potential bonding with DNA. So just a little background information. Transition metal complexes, again, interact through DNA with several methods. Covalent bonding, electrostatic interactions, groove binding, and intercalation. For this specific research, we're not sure what the exact type of bonding that occurs. The fact is we really don't know. It's not really proven, it's not demonstrated, and it's very difficult to really ascertain the exact type of bonding. Real-world application of this type of property is in platinum-based anti-cancer drugs. It's a very common chemotherapy use, and I suppose ideally there would be an application for ruthenium-based anti-cancer drugs, although the fact is you know, I'm not here curing cancer, but it is a potential. Experimental materials and methods. DNA was PUC-18 from Bayou Labs. Agarose gel, which was composed of agarose and 30 mils of tris-base buffer, which is made up of a tris-base and boric acid. Gel electrophoresis was completed at 100 volts, 200 milliamps for 90 minutes. The staining of the gels was completed with ethidium bromide. Photolysis was completed using visible light range, and that's very important to only include visible light range because exposure of the DNA to UV light would cause premature destruction of the DNA. And incubation, which is conducted in 37-degree water bath, again, a 30-minute exposure. Just to kind of liven things up, I got some pictures of the devices that we used. This is the device to run the gel electrophoresis. Here we have the exposure of the DNA to a light source. And last is the water bath shown here. Experimental results. As I alluded to, the initial results were not in line with our expectations. Neither of the molecules demonstrated any correlation of DNA binding to incubation or to photolysis. What we did find, somewhat by accident, was that there was some sort of DNA binding that was going on that was a function of increased exposure time to the metal complex. The BPY molecule was the one that displayed this property. So here is the gel that we run. This was July 16th. On the right-hand side, you see all of the molecules, as well as was this particular sample photolized, was it aged for 24 hours. The column that you really want to look at is going to be 4 and 5, or rows 4 and 5. But first, I want to just kind of explain what you're seeing here. The first row and the 10th row are the control samples of just pure DNA. And what we have is, I'm showing you the supercoiled band as well as the relaxed DNA. The 4 and 5 is what you really want to see. You can notice that they're a little bit different than all the others. So what we have here is displaying a streaking effect, indicates that there is some sort of binding going on with the DNA. This was the second gel that we ran. Now this one has DNA that was aged 168 hours. It was from the first gel that you saw, which was run on the 16th. It also includes DNA that was aged 2 hours with the metal complex. Columns 2 and 3 are the 168 hours. So there you can see that this increased streaking has pretty much obliterated all of the DNA that was in the sample. And we're also looking at columns 3, 4, 5, rows 3, 4, 5, in which you can see a very slight beginning of breakdown of the supercoiled's DNA, resulting in that middle band right there. So the results that we got raised several questions for further investigation. The first step was to determine is there something that we didn't factor into the equation that is causing these results? So we had to measure the purity. We did so by using electrochemistry. The results were satisfactory enough to justify further experimentation. Going forward, we need to look at continued analysis to determine the exact mechanism of the observed results. We are looking to complete a second synthesis of the ruthenium molecule so that we can repeat the experimentation, see if we can get the same results as we did over the summer. We need to look at designing further experiments using exposure time of DNA to the ruthenium complex so that we can assess the nature of the binding in further detail. And there's also going to be ongoing experimentation of other asymmetric ruthenium molecules to assess other DNA binding characteristics. So with that said, I'm ready to complete my presentation and open up the floor to any questions that anybody might have. No questions.
Thank you for very nice, was there a question?
Doesn't seem so.
Very thorough presentation. Sounds like you really got into some deep analysis. I appreciate the hard work that you did. Thank you very much.
Absolutely, thank you.
So before we get the next pair of people up here to report on their work, I just wanted to introduce a couple of other people. Elizabeth Ramos, who is the overall director of the STEM Pack project. She's the one who's responsible for all the good things that happen, and she gets to deal with any difficulties that we run into as well. And she does a wonderful job. My name is Jim Lerman, and I am the director of the STEM Pack project here at Kean. For those of you who might not be very much aware of this, the STEM Pact is a joint effort between Kean and Union County College, or between Union County College and Kean. And our ultimate objective is to make it easier and more efficient for students to transfer from UCC to Kean. And we also want to support those students when they make the transfer to stay in school and finish their degrees on time. And we have some very elaborate structures that we've put together to try to encourage those things to happen. Our next two presenters are going to be Catherine Cabrera and Gustavo Arias. Can I have your flash drive to plug in? Great, thank you. Who wants to drive this thing?
The laser is this one, right?
Yeah, it does work. But it's that button, yes. Oh, and please use the microphone.
Thank you.
Recording this. I don't see anything in the drive. There we go.
There. Scared me a
Scared
little
you.
bit.
You just scared them.
Biochem presentation?
No, that's the last one.
The last one.
Correct.
So this is what's up on the screen. This is what's next.
Correct. Oh, you're getting a second.
Good morning. How are you? My name is Gus Arias, and I am a current Union County College student, and I am majoring in mathematics.
Good afternoon, everybody. My name is Catherine. I graduated at Union County College the past May. Right now, I'm taking a break due to financial problems, but I hope I'm coming back for the spring to pursue a mathematics education major. And probably conjoined with a master's as well.
Our faculty mentor for this project was Dr. Pablo Zafra, and our research topic is solids of revolution rotated about oblique lines. So in integral calculus, we use integral calculus to find the area under a curve, as you can see from that light purple graphic. And we use this formula, which is area is equal to the integral from a to b of f of x dx. And we also use that Cartesian coordinate system to revolve set functions about either the x-axis or the y-axis, or horizontal or vertical lines which exist in that xy plane. And yeah, as you can see, those are the graphics.
However, there was a variation to the problem, which was the problem presented by Dr. Zafra. The variation is, what if we don't have a horizontal vertical axis? Well, what if we're not rotating around the x or y axis, but what if we're rotating around a slant line? And to be more specific, what if we're rotating around the line y is equal to mx plus b? This becomes a whole different problem. And it was our job to see how we will find the area, how will we find the volume, I don't know if you can see me, if the axis is not the typical thing that you learn in a calculus class. So the approach that was taken was pretty much, first of all, it had to be geometric in order for us to see what we were doing. And then it involved a lot of algebra and a little bit of trigonometry. Oh, no, wait, let me go back. For example, there we have a sample function, f of x. Right there, this is f of x, the curve. It's just I took any curve just to sample everything. Then the red line is the y is equal to mx plus b, which is our new axis of revolution. So this pretty much what you're looking at is the representation of the entire problem that we were working on. This is a pretty much more detailed sketch of the approach. It was possible to do this only if we took the tangent line at a point. Because of the tangent line, everything that you see there was possible to draw. You see a lot of rectangles, triangles, and based on that, it was possible to come up with these two formulas. There is a connection between all the angles that are there, between the du and the dx, and that's what the first approach is. There exists a connection between the du, the width in this axis of revolution, and the typical width in an x-axis of revolution. And through algebraic and trigonometric approaches, these two formulas were found, the area and the volume. Probably if most of chemistry students and biology students, I know they take calculus, especially calculus 1, and it's very similar to the typical area and volume formula. The only variation, this m squared plus 1, comes from all this transition from the du to the dx. And this f of x minus b comes from the subtraction of the f of x formula minus the mx plus b of this to obtain the height. So everything is this approach is the translation of the typical problem to this variation of a problem. And the volume, as you can see, it's also similar to the way we find the volume today. It still has a pi, it's still square, because when you do a solid of revolution, it's based pretty much in the area of a circle, pi r squared. Hence, we have the pi and we have the square. Everything is a relationship, but this is pretty much a formula that lets us integrate with respect to x. I know it looks a little bit tedious. It is kind of problematic to do by hand. Actually, let's say if I give you a problem, find the area of the curve, a linear curve around this axis. It becomes such a huge problem that pretty much by the end, if you have a complicated trigonometric or even a longer linear function or polynomial one, you have to rely on a calculator. There you go.
Furthermore, aside from that first approach, which utilizes just the function, and aside from the first approach that just utilizes that geometric representation, we have, in terms, I guess, a better approach in the sense that it doesn't utilize all those lines and all those triangles to make that connection. Instead, we have this second formula, which is based on the rotation matrix. We know that a function is a collection of dots which are graphically represented by curves on an xy axis. And with the rotation matrix, we can rotate that axis which is shifted. You can't see it because there's no graphic of it, but we can shift it from that, I guess, an x prime axis, that shifted axis, to our regular x axis, and therefore integrate as we usually do. What was I going to say? So this is the formulaic structure of this second-hand formulas is very similar to the first, and the only variation really is in those trigonometric expressions which replace the f of x and the m and stuff. Yeah, and yep, that's it.
And just to add a little bit more onto that one, and just to pretty much kind of connect what we learn at UCC and what we will keep learning as math majors, you learn this in linear algebra, the basic way of how to rotate a point by theta degrees. And also it's also used in other applications such like computer graphics when they rotate a whole image, pretty much the whole points of the image to, let's say 45 degrees. But the problem is that only a point, we didn't want to rotate only one point, we wanted to rotate the entire function. So the matrix was applied to the entire function. And all of this, and the tangent inverse of m, they were all obtained from the first approach, from the connection between the du and the dx. There was no other way to get them without the sketch pretty much. So the two approaches kind of started in the same, they followed the same half, but then the first one continued on and this one carried on its own life. It continued, but it took this linear algebra approach to come up with this formula that may look different, but at the end gives you the same results. And in an example that we have, it gives you the same results like up to 4 decimal values, which is pretty accurate. Okay, so just to visualize everything, we have an example. It's the function sine of x plus half x plus 2, revolve around the line of y is equal to half of x from 1 to 5. This is what it looks like. The shaded part that you see there is the area that we want to find. As you can see, it's not with respect to the x-axis. It's not that simple. It's actually perpendicular to the axis of revolution, and all those, let me see, all this connection, the connection from here to here is what made all of this possible. If you visualize a volume, you just visualize about something rotating, and that's what it will look like to you. But if you need a little more visualization, this is a 3D image of what it would look like if we were to rotate something around the slant line or the y is equal to mx plus b line. So I hope this image helps you visualize what we're looking at, because it's very, you learn that in calculus, you learn the basic rotating around the x-axis, the y-axis, but it's really good to also think outside the box and look for other problems that make you think. It's simple. You might not see this for example, in a calculus book, you're never gonna do this problem and rotate about this. It's just a variation, and I think that's what makes you think outside the box and use what you already know for something else. There you go.
Okay, thanks. So with that being said, you see our first approach formulas here, which are those formulas that had f of x minus mx minus b. Times 1 plus m times f prime x dx. And since we are utilizing sine of x plus half of x plus 2, we have that here. And then we have replaced, obviously, everywhere where there's a function sine of x. And then all those substitutions are made. And also here we have our volume formula with the same substitutions made for the sine of x, the same function. And for our second approach, our theta is equal to so the same angle. So now we utilize those second formulas with this, the second approach formulas. And as you can see, this is longer in length than the first, but the same amount of computation is needed. So the first is as tedious as the second. So even though it looks longer, it's the same work really. And yes, that being said, this this tediousness in computation is what makes it necessary to use computers and math software to perform these calculations for us. Because even though this is a very simple function, there are very complicated functions which require that math software. So yes. As you can see, this is the area that we have obtained from these formulas, and this is the volume, and they are correct to about 4 digits.
All right. Okay, so one more. The overall experience. We explained 2 approaches here, and that's what math is about. There's not only one way. You can tackle a problem different ways. Like, for example, with my brother, I want to be a teacher, and I was looking at yesterday, I'm like, when kids are adding, you tell them, 8 + 3 is 11. You write the 1, but you carry the 1. And nobody ever tells them, why do you carry the 1? I know it's something simple, but it's something that you need to know. And I know there's also a lot of algorithms for adding. They add the 1s, they add the 10s, they add the 100s. They have the lattice method for multiplication, things that I didn't learn. I only learned one straight method when I was back in middle school. And I took it as if it was given to me. You do this, you do this. I was taking steps. I was following instructions like as if I was a machine. I never questioned, why am I doing this? And that led me to that exploration that I have done with this research project has led me to think that there's more than one way, and everybody needs to know how to take second approaches or even third approaches to the same problem and know why are they doing every single step, not just accept as if it's correct. You should always question what are you doing. And that's why we had 2 approaches here to show that you only have one way. You have a second way, and that you must follow to be aware of all the possibilities that they're out there. Oh, okay, never mind. I'm not done yet. Sorry. So also another thing is, for math, you need computer science. You definitely need it. I always said I want to be a math teacher. I'm always going to study math, and that's it. But then I'm like, this computation is going to take me 1 hour. I need a computer. I need to learn how to program. I only took 1 Java programming class, which probably would just allow me how to create a basic calculator, which could only add and subtract and multiply, but I had no idea how to make a program that will integrate, and especially integrate with respect to this line. And I know that there's a gap there between mathematics. Math lab, Sage Math, everything has to be taught for math majors in order for them to have like the full package when they're doing research or when they want to teach something. You also need to visualize stuff. You need software that will graph things for you, that will show you something that might be very difficult to visualize in your mind. And that is very important, and it was a difficult thing in this research project, getting familiar with the programs. I had to download a lot of programs. I tried to find the cheapest ones or the free ones, and I know some that were 500 for students, which I couldn't obtain, but I went to the free software, contacted people that told me which ones were free, which ones are good, and that's also the importance of networking. I contacted a geophysicist from Texas who did a research project similar to this problem back in 2011. He told me to use this software, Sage Math, which is a free software, and thanks to that software is the graphics that you're seeing there. Otherwise, I had no idea how to do them. It is important to contact people. It doesn't matter if you don't know them. I had no idea who this person was, and I Googled up his name, his LinkedIn account, and I had to lie that I knew him on LinkedIn to be able to get in contact with him. Then once I lied that I knew him, I was able to, I'm like, this is me, I'm trying to do this, I need to know what programs do you use, I'm not aware with them. And he told me this program, I use this program, and a very nice person, a person that I didn't know, and we were exchanging emails, and pretty much made this whole thing possible, especially the graphics, which I would not know how to do it by myself. You can continue.
I had a very different experience in Catherine, because the people I emailed for their material did not answer. Yeah. And that's fine. That's part of the experience, I think. It's about finding that independence to undergo this research, and the independence to continue forward in it, because it's not it's not like school. It's not, someone's not instructing you. I mean, our faculty mentor did help us, and he did instruct us. He did guide us. But when you're trying to find something that doesn't exist or trying to grab something that's original, it's not easy. It's not, you have to become more than a student. You have to become an explorer. And with this experience, I learned that I needed to become a lot better at everything that I did. I needed to study a lot more. I needed to be more prepared. I needed to have more passion for what I'm doing, and I need to stop being lazy. Yeah, I'm very lazy. And out of everything, I think I just learned from my mistakes. I learned from things that I did wrong, or I just saw the things that I was missing, and this experience has really made me hopeful and has given me expectations of the person, of the academic that I want to be, which is a prepared one that is always knows what to say, and and furthermore, this project, this research has given me a scope of what it's like to be a researcher. It's not easy. It's not quick. It's very tedious, to use the word again, because I can't think of a synonym. And these researchers, these people that we study in these textbooks, they're really brilliant, really, for finding these results on their own. It's original, and I don't think with my current capabilities I could do that now, but it just gives you that sense, that admiration of, really, these people did it by themselves. They had no instruction. I mean, they did have instruction, but their results were found on their own, and that is why I'm grateful for this experience, and I want to thank Kean University, and I want to thank it for lending us its faculty and its resources, and I want to thank Mr. Lerman for his very nice introductions, and thank you for everything.
Thank you.
Thank you, guys.
All right.
Any questions or comments?
Oh, yes. Any questions?
Okay, please, if something occurs to you, please feel free to get the students after the presentations are over and grab them by the collar and say, what about this and what about that?
I'll take it on. It's a little bit different than mine.
Just, yeah, you could drag it, my trash is over here, drag it to.
That's it?
Yep.
Hope it's safely.
Very nicely done. Great, thank you. Kimberly and Shaznike? How close did I come?
First part, the second part.
Say it for me right. Say it for me correctly. Shaznike?
Nika.
Shaznika?
Yes.
Okay. Have you worked with one of these before? Okay. This goes forward. This goes back. This is the laser pointer.
Okay.
And just hold it down. You're welcome. And please use the mics.
Okay.
Because we're recording this.
Oh. Let's play from start, right?
So this shows you what's on the screen. This is what's coming next.
Yeah. You want me to press or you want to press it with you? Okay. Yeah.
Go on the side. Good afternoon.
It's not amplified, so speak up.
Oh, okay. Good afternoon. My name is Kimberly Joseph, and this is AKPU. So this summer we had the opportunity to do a research conducted by Dr. Fried. And what we're trying to do, we're trying to express engineered cellulosome for bioenergy applications.
Okay, in Exhibit A, that's a picture of the enzymes on the document, and it shows how they're attached. And then they're attached by the protein and then to the bacterial cell.
And the second image is basically to show you the one of the gels that we run in the lab. We're looking to find the purity of the protein. Okay, so this image is basically what we're working with. This is the coenzyme dockering. This is a module that is the major building block of what we know as scaffolds. So what we're trying to do basically, we're trying to use cellulosic waste. We all know that cellulose is made of sugars. So we're looking to find a way to use cellulosic waste. We make soluble sugars, and then from the sugars we will make ethanol, and then from the methanol we will make biofuel or biodiesel. But the thing is, we're using engineered enzymes, and what is unique about this enzyme is that they are made with the dockering coenzyme interaction, which is the one that allows to design multi-enzyme complexes. Now I'm going to talk a little bit about what we did in the lab during these 8 weeks. The first thing that we did, basically, we were using an engineered E. coli bacteria that had a DNA inside, and which was specialized to be expressed. The first thing we did, we tried to inoculate this bacteria by using an agar plate that had ampicillin, and then we let it grow overnight. And the next day, we picked 2 colonies from the plate that we prepared with bacteria. And this plate, from the growth of the colonies, we picked 2 cultures that we made with LB media. And the LB was what we used to keep the bacteria alive and fed. And then after that, we put it in the incubator that spin, and then that produced even more growth. And the next step was to have the protein expression. And for that, we used the IPTG that was used to induce the expression of the protein overnight. And after this overnight expression, we used a lysozyme that was put in the solution so that we could break the bacteria open. And after that, we will centrifuge the solution, and then we will have 2 parts. We have the insoluble part that will be at the bottom, and then we had the soluble part that was on the top, and that's what we used to purify, and we stick it to the nickel beads. Now, the nickel beads are what we used for affinity chromatography, which is a method known for separating biochemical mixtures based on highly specific interaction. And these nickel beads, what they had that was really like amazing about them was that they will only stick to the protein that we're trying to express. And finally, the last step is what I shown before, where we were trying to run a gel of the protein, and then that would tell us how pure the protein was.
Just a little background information for the cellulose. It's one of the, it's very abundant in our environment. But the thing about the cellulose is that during the, sorry, kind of tongue tied, I don't really like talking. During the disposal of the cellulose, it's burned. So the waste is burned, so it's not able to use in our environment. However, through the cellulitic system, it can be converted into glucose, which can be used for a lot of genetically favorable processes. And through these processes, like we said previously, that it could be used for the biofuel, which is like ethanol, to be used for like, cars, machinery, and things of that nature. That's basically over. Okay, this picture right here is actually the cohesin dockerin, And it's actually we created this diagram in a program called PIMO. That's another thing that we actually learned during the summer how to use, and we created this this structure out of the enzymes, the different characters of the certain enzymes, and this shows the crystal structure and of the two proteins put together.
So these images kind of sum up everything that we're talking about, where we're saying that at first we have the cellulosic waste, and then from that we can actually, so from the cellulosic waste we can have the cellulose degradation that will give you soluble sugars, and then the sugars we can use that with the fermentation in bioethanol raffineries that will give you biodiesel or biofuel for cars and everything else.
Okay, this basically sums up, the whole project. What we did is, at the conclusion to the project is that we went through the whole process of the experimentation, and we got to a certain point where we stopped. And at that point when we stopped is because when we actually abstracted the bacteria, it was shown that it wasn't purified enough. So at that point, just like, and I guess in all you guys, you're all teachers, so you all guys did experiments before, when you do research, how you get to a point where you get to a roadblock and that's it. So basically, the conclusion was that at three different points, we stopped at the purification point where we couldn't go anymore, and then we had to go back to the drawing board, and it was like, I guess, the returning process of, just a circle of things that you had to do.
So that was the team that we worked together for around like 8 months. I can say 8 weeks. But, I would say that I learned a lot from Dr. Fried because that was my first time working in a lab, and I learned how to be patient because sometimes we do something and we have to do the same thing over the next day because what we're looking for, that's not what we found. And also, I would say that I learned how to be very cautious because you cannot touch everything. It's not like when you're just doing, I wasn't used to that. And Dr. Frida had to be very careful with us because we're touching everything. And he had to tell us that we have to be careful so we don't infect anything because we wanted to have the result that we were looking for. And
this summer was a very good experience. On the other hand, there was 2 aspects where I enjoyed the summer. I worked with Dr. Fried in the lab part, but also I actually worked with him in the upper bound part as well because during the summer I was taking classes the whole summer. So my schedule was not too flexible. So I would come in, in the beginning I did work with them a lot in the beginning, the lab part, but then I would just come in later for an hour or 2. But then he allowed me to come and help him with his other projects he had going on, so which was a great benefit to me as well. I got the lab experience because, certain things when you learn in class and learn in books, you don't really get to utilize them until you work in a lab. Like different pipetting or certain ways of, certain aspects of things when you learn in a book, unless you do it, you don't really know you don't really know it. You're just reading it and learning it. But when you're actually in the lab, you're actually doing it. And that was the part that I liked for the lab part. But also, when I worked with him in the classroom setting with the high school kids, I'm actually an education major too. So that part actually was, important to me as well because I was actually glad that he let me help him with that because that allowed me to just work with the kids and see what he was doing as far as creating lessons and showing them what they need to do. And we also ran through some of his labs that he had prepared for the semester, so that helped us, just get a feel of what that had to be with that as well. So this summer was a great benefit of both parts of lab work and as far as, a teaching aspect, because I got to work with students and see from his point of view how long it takes to actually create a lab. Because when you get into a lab, when you're in a classroom and you go to a lab, you just go to do the lab. You don't understand how much it takes to create the lab and, the kinks of the wording and if the lab process is going to work out properly or if everything's going to be the way it should be. So that aspect, that was really important to me as well. That's it. And it was a great honor working with Dr. Fried. He was, sorry, I had so much fun with him. He was very cool and relaxed, so he was a very good teacher, and I really appreciate the honor. Thank you.
And we'd like to thank everyone because that was a great opportunity for us because we learned a lot and Thank you, Dr. Freed, for everything. Do you have any questions? Any questions?
I have one.
Yes.
So what do you think about the future of cellulose as a biofuel?
Well, I think it has great benefits. I mean, as long as we able to engineer those things, it has, as we have shown in the lab, when we did our work, and the things that they were shown, it has great benefits to actually, it's a great product to be used, because you can use it for so many different things, and it's a natural source.
And it's
not-
cheaper.
I would like to add a comment. In reality, cellulose is currently there's a process to break it down, but it's not environmentally friendly. It's
I
using
see.
acid, and I think there's a plant in China that does that, but I don't think it's the most convenient thing because we want something that is not going to damage the environment more. We're already damaging too much by trying to get oil from the ground and all of that. So that's the most important part, breaking down the cellulose. Cellulose is, I don't know, probably the waste of plants, I don't know, from corn, is everything else that we don't use from the corn. So everything, all of that is going to be thrown out. And instead of throwing it or burning it, degrading it into simple sugars is the most important thing, but there's a lot of drawbacks. The cost also. The biodiesel, there's ethanol, for example, it's not a so popular source such as gas, because with this process it will be extremely not cost productive, it will be extremely expensive to make for the price of ethanol. So that's why I think I also work with them, that's why I say
Yes, she's right there.
that's why I was so curious, does this exist? It does exist, but it's not good for the environment. And this process will make an entire breakthrough in science because breaking it down in a cost-effective way, which probably will be very difficult to obtain. First of all, breaking it down will be a great achievement, but then making it cheaper will be a second. And I guess it was really important to work with it, but if this project continues, which Dr. Freed said that he will continue on this project, and we can volunteer, we can come back with him and work through the fall, the spring. If that actually happens, I think we will make a difference.
Great, great. You know, that gives me a chance to talk about this place that we're in, this Human Rights Institute. I was very excited. I was hoping that the director of the Institute would be able to join us today, but unfortunately she wasn't able to. The description of how a possible solution to a problem also may create other problems that need to be addressed, and sometimes the so-called solution may be a worse outcome than the way things were before. And there are certain aspects of that relate to human rights issues. I think very clearly, there's a lot of health issues related to what you were talking about.
Specifically, like we produce corn. It is already an issue whether the corn should be used for food production or for this ethanol production. So we rather use the waste of corn and give the entire corn for food production.
Right, and we pay farmers not to grow the corn, which is interesting. Well, thank you for bringing up a very good topic.
That's right. You have it?
Okay, so we have our fourth presenters. IJEOMA. I got some coaching beforehand. IJEOMA, AKPU, and SHARON NAKAFERO. How'd I do with your last name?
It's okay.
Well, tell me how to say it right.
Yeah, you saying it right. You did.
Oh, okay. Okay. So do you have your flash drive? Okay, great. Where is it?
Or research. Research. And then open this one.
Top one?
First one, yeah. And also silver. I need that one, and then I need another one.
You need another one? Okay, so I gotta go.
And solvent.
Okay, so you're gonna go this first, and you know how to do it?
Yeah.
To get, okay, great. So we're just gonna start the slideshow. This is forward, and this is back, and this gives you the laser light. Okay?
Forward,
Well, you know what? Then you go the other way. And please use the microphones, because it helps us to record it better. Great, thank you. Yes, it's on.
Thank you.
Is this one on too?
Forward.
Yes.
When I say these,
Good afternoon, everyone. My name is Sharon, and this is
IJEOMA.
So we had a good opportunity to work with Dr. MANDY BENNETT. And we're from UCC. I'm a bio major.
I'm also bio major.
Okay, the title is Extraction of and Environmental Analysis of Parrot and Cockatoo's Livers and Kidneys.
That's just our names.
Those are the authors.
Just our names.
Okay, the abstract. So this study, we had like to collect livers and kidneys from the parrots, such as the Amazon parrot, the African gray parrot, and the cockatoos. So we had to get the kidney and liver, and then we'll analyze it as an indication for looking for novel organic molecules that may prove to be biologically active and the key to parrots' long lifespan. So we'll also try to look for the elements such as chromium, arsenic, lead, and mercury. So those will also be like, we don't really know if they'll also like acknowledge for the longevity of parrots, but we just want to try out and see if they are responsible to how parrots live a long lifespan, because some of them live up to like 100 years. So we did not do a research on all parrots. We just have to pick particular parrots because they are large and they live longer than others. So these are the parrots.
This is the African gray parrot. He lives for about 50 years, and he's from 12 to 14 inches in length, and he's mainly found in Central America. This is the macaw parrot. He lives up to 60 years, and his length varies from 30 to 36 inches. He's one of our biggest parrots in this research, and he's mainly found in Latin America and Mexico. This is the Amazon parrot. They're my favorite. They're so pretty. They live about 60 years, and they range from 9 to 18 inches. They live in also Central America.
And this is a COCKATOO parrot. I just like it because it's bigger. It's one of the biggest parrots. It's found in New Zealand, and it lives up to 70 years old.
Just up close picture. This is my favorite. I call him Jafar. This is the palm. This is the palm cockatoo. He lives up to 70 years or more, and he's found mainly in Latin America, Mexico, Western Australia, places like that.
I call him the evil because he just looks evil.
Okay, this is our cockatoo. This is the Kean cockatoo. He's one of the one that lives very long, so up to 70 years or more. He's 20 inches, and he lives in eastern Indonesia. This is the sulfur crested cockatoo. He lives up to 80 years. He ranges from 15 inches, and he lives in northern and eastern Australia. This is the prettiest one to me. He's so pretty. This is the major Mitchell cockatoo. He lives up to 100 years, and he's 14 inches long, and he lives in central and western Australia as well. Okay, we didn't get to do an experiment because we never got a parrot or a cockatoo. They didn't come through the mail. And so, but we did get to practice what we would do with it. So we use these things. We use beakers to pour solvents in, LMI flasks, pipettes, funnels to filter out certain things. We use 3 molar HCl, and we use certain pellets that would help dry out water from organic compounds. And then we use the GC mass spec, which is short for gas chromatography mass spectrometry. And then we use something called the nuclear magnetic resonance. It's an NMR machine that helps you see peaks of organic molecules. Same thing with the IR, the infrared spectra. It does the same thing, just it looks different. So you can see 2 comparisons. And then we learn how to extract organic compounds from different things, from a mixture of things.
Okay, we have the protocol, what we're supposed to do. Okay, how can I make it bigger? We didn't do the introduction of the background. Okay, I'm gonna do it. Okay, thank you. So we're working on parrots, so we say, and the cockatoos. So basically, how did Dr. Mandy Bennett come up with this research? She found out that a lot of scientists had done research on mammals and animals that live for a long time. For example, the sharks, whales, crocodiles, and many others. So she was curious, what other animal or birds live for a long time? Even though some scientists had done research on parrots, mainly they searched on proteins and lead as an element. But no one had used the extraction method for other organic molecules that might be responsible to why they had longevity, to live up to 80 years, 100 years. So, and that brought us to a question in consideration. How are the organic molecules with parrots and cockatoos' livers and kidneys responsible for their longevity and strong immune system? And this is the table that we had. So basically we had to divide the kidney into the left and the right, and the liver into the left and the right. So for the kidney, we had to put it in water, distilled water, and stir it. And then, okay, give me a minute. I don't know.
Okay, there we go.
Okay.
No, sorry, sorry.
And then we had to extract it with ether, ether mixing or the pet ether. And then we had to pre-distill it and find out if there were any non-polar solvents. And then for the other half left kidney, we had to chop it and then stir it. How do I do that? You do it. Yeah. And then we have to acidify it with hydrochloric acid, the HCl. Then after that, we had to precipitate the organic acids. So after that, then we'll extract it with the TBME, polar solvent. And then after that, we had to dry with calcium chloride, and then filter it, evaporate, and then analyze. And then for the liver, we had to also filter it, put in this water, acidify it, and then extract with a TBME. So most of you are wondering what is the TBME. The TBME is like T-butyl methyl ether. It's an organic solvent. And then we do the same process, dry, filter, and evaporate, and then we analyze. So the same apply to the, sorry. The same apply to the liver. We had to mix it with TBME and then dry with calcium chloride, filter, and then analyze. Yeah. So at the end of the day, that's what we're supposed to do when we got the livers and we got the liver and the kidney from the parrots and cockatoos. At the end of the day, we're trying to find out like organic acids, if there were any presence of organic acids, and then organic solvents. So the experience of before I do the parrots, yeah, some people stay with parrots, so they are pets or cockatoos. But at the same time, we have diseases that are transferable from parrots to humans. The TB, avian TB, parrot fever, candida, cryptococcosis, and avian chlamydia. So basically for the parrot liver, if you inhale dust from and their droppings and basically handling infected bats, that's how you get infected. Yeah, it can be treatable at the same time, but so if any bat in any parrot or cockatoo, if we were to get any parrot which had disease, we could not allow it, like we could not work with it because they are easily transmittable if you had that disease. Experience.
So in my experience, I love doing this. We decided to come back and continue with Dr. Bennett until we get a bird and actually do the stuff to it. So we'll come back. We'll come back and we'll still see her and be with her. But I love doing this. It taught me a lot. Because when I first came here, I thought that I would come here, there'd be a bird ready, we get stuff rolling, and it'd be great. No, it's not what happened. We had to mail about a lot of letters, the vets, to zoos, to
Hospitals,
adoption centers, to try and even get one to answer us about getting a parrot. And that took up most of the weeks because no one answered us back. So we're still waiting. But I did learn to be patient, very patient. And that a lab is one of the funnest things to do. And I'm so glad that I'm in this bio career because I love to do this. It's a very passionate thing that I'm passionate about. And I'm just thankful that I got to work with her. She's so awesome. Thank you. Oh.
sorry. So this was a wonderful and exciting experience that I look forward to each day. So when I came in, I thought, yeah, the same thing. The parrot was ready. We go in there, work with the parrots. But no, that didn't work. So you had to do research on hospitals, looking for veterinary hospitals, looking for doctors and everything. But yeah, we'll get back to you when we get our parrots.
I don't know what happened.
So coming in here, the first question is, did you guys do organic? We were all like, no, we didn't do organic. But for me, I did chemistry 105, which is partly the inorganic and the partial organic. So I had the basis, but even though I had the basis, I could go in there and she started giving us the NMR spectrums and we had to find out. I'll get stuck. She's not a person who would tell you, okay, do this, I give you this example, and then you do the rest. No. You had to think outside the box. So the first few days I'll be there stuck. I'm like, oh my God, what am I gonna do? Because I'm this person, give me an example, I understand you, then I'll do the rest. It was different. So I had to think out of the box. And finally, when I got the answer, trust me, I was so excited. I'm like, Dr. Bennett, do you have other exercises that I can do? Do you have those examples? I was so excited. So I learned that you have to to think out of the box. You have to leave your comfortable zone and stay out there and think really hard. I learned that you don't have like quick, here we go. You have like to take a slow pace at a time. Usually I'm panicky in the lab. I know what I'm doing, but I doubt myself. But this was hands-on, so you could see me when I went up the ladder to put in the, it was a specimen to put in the MR machine. I was so excited. I had this huge smile on my lips. And she looked at me, look at her. She's so excited. I was so excited. The other thing is usually shy around new people, so I had to get out of there to be myself and do this experiment. So basically, I learned a lot of studying on organic chemistry, and I'm looking forward to organic chemistry because I know I have like the basis. And then I'm friends with Dr. BENNETT. I'll be calling her. We told her we'll be calling you if we get any difficulties in organic chemistry. So yeah, now I'm up there looking forward for organic chemistry because I had a wonderful experience. I looked forward to, and yeah, I'm gonna continue working with her. Any questions?
What application is the
What do you mean?
like pharmaceuticals, developing pharmaceuticals from like the longevity of the parents?
But
Well, not
Yeah, we didn't do it, so I'm like.
But we're thinking that if we are able to find anything, maybe it will be used to humans in a different way, how to help them like live a longer life and everything. So you know how science it is. You just put a hypothesis, I want to do this, but that's not what you get at the end. It may be a different result, which may also be useful, but yeah.
Any more questions? That's
I
it.
did,
Oh,
just to follow up, so the initial is really looking at sort of contaminants within the
and
animal.
like yeah,
Yeah.
So something that may actually be reducing its health or its longevity.
or increasing its immune system.
Oh, okay.
Because parrots are known for having a strong immune system. So what we are looking for organic solvents or elements that are responsible for that.
Oh, they were responsible because it has such a
Yeah.
strong.
Yeah. So after that, maybe if we find which organic solvents are or elements, then maybe there will be another wonderful scientist who will be able to put it into medicine, help humans with living a longer life or reducing a disease that they have, anything like that, treating a disease.
Got it. Oh, one more.
Stronger is the parents' immune system.
Oh, they are really
Most
strong.
parents don't live to be like 20, so for one to live to be 100 is incredibly strong for just for a bird. Most animals don't live past human life, but these birds can, which is incredibly amazing. So that's why we chose these birds. Is that it?
Terrific.
Okay, thank you.
Thank you. I'd like to turn the tables now for the professors. I'd like to ask you to say a word or two about what this experience was like for you, what it was like working with students who were not from your university, anything that occurred to you surprisingly or any other way that happened during this experience that you'd like to share with us and with the students that you worked with.
I think I'll go first because I have to run to a class.
Okay.
But yeah, I'm really thankful to the 3 people who are here who helped me actually get my lab set up this summer. So I didn't have a lab when you guys started, and then when you were done, it was all set up and it was functional, and you guys really helped me out a lot. Actually, so you guys got something, but I also got a lot out of it because also it motivated me to actually go into the lab and start the work that I need to do. So thank you guys also. And keep it clean, right? And keep it clean, yeah. Yeah, it would have been Hoarder's paradise in there if it wasn't for these guys. So yeah, so I think I got a lot out of it also. And it was nice learning to manage a group of people and make sure everyone has something to do. And yeah, so thank you guys also.
Great. Anybody else? Matt?
So it's a.
Oh,
Go ahead. You sure? It's nothing. It's nerve-wracking enough to do research, but then when you get asked to do research with someone you've never met before, it's even more nerve-wracking because you don't know what you're going to get. But in my case, I was very lucky because Mike came in with a lot of experience and a lot of drive to do well. Especially when I got a bio major. Oh my gosh, what are we going to do? No, I not feel lucky, but it turns out I was lucky because Mike likes chemistry, and that really helps a lot. So it's, but it was a great experience. Mike was an incredibly hard worker every day. He was there before me, which is not hard, but he was there before me, ready to go, and was very self-directed, and it was really a great experience. I really enjoyed it very much, and I'm very grateful to Mike for all that he did this summer. And he actually kind of rejuvenated we didn't mean to, but he actually kind of rejuvenated the research I'm doing, because the data he got looks nothing like anything we've ever seen before with the molecules we're working on. So it kind of re-kickstarted my want to do research too. So it's been great. I do a lot to Mike for that.
I just want to add that what I found interesting in my experience, that motivated students are all the same. I mean, these are not my students, but yeah, when they come approach me, I felt like they've been my students all along. They're not majors here. I'm so proud of the work that they've done in the summer, and sacrificing a couple of months just trying to gain some knowledge. Students are all the same, and it's something that I found really interesting.
I'm walking to Kean to have
Mandy?
It was a great experience for me because they started from like where I needed them to be, and they worked towards getting to. Now they're ready to start. When we do get the sample, I won't say when, because they're ready to go, and they have evolved, and they started out like, and then they learned to go with the flow, and which you have to, as everybody in as family knows, you have to go with the flow. So they really come a long way in a short time, and it's been a good thing to see. And they helped me with cleaning up the lab that I get to work in, and if you've seen it before, they went in there, and you see the fume hood now. It's a whole different ball game. So I think they're going to keep me on track with that one. And I was getting very disillusioned, to say the least, especially in the middle of summer, and they kept me going, because I really believe that even if we find nothing in there, this is something we should be looking to see if there's something in there biologically active that could be used medicinally for us.
Well, I want to thank everybody for coming today. This was a wonderful sharing experience. As someone who had a hand in organizing this thing, really have to give a lot of credit to Liz Ramos and to, Amber Pantoliano, who did so much of the work for organizing this experience. We will be doing this again next summer with more students and with more professors, and we hope that we'll be able to call on you guys to help us recruit students into the process, and we may call on you to come back and give further presentations, perhaps not so formal, but to talk to folks about the experience and what it meant to you, and what you learned and what you got out of it, and where you hope to take your career as you go forward. It's very likely that we'll be reaching out to you again to come back and talk with us some more. Sometimes it's very good to be the first one to go through a program, because we pay special attention to you. Everybody's special, but the people who come first are special. So that's a wonderful thing, and I think we'll be coming back to you often for your thoughts and your advice, and to keep track and try to encourage you to keep moving forward. I noticed that we were joined somewhere during the presentations by Dr. George Chang, who's the Dean of the College of Natural Applied and Health Sciences. George, I don't know if you want to say anything.
Our makerspace is going to be grand opening. All of you are invited to join us for the grand opening. The date is set, right?
October 21st from 5:15 to 6:45. One of the reasons why I have the sign-in sheet is so that I'll be able to communicate with all of you. And we'll be asking you to join us at that, and maybe make little mini presentations along the way. And there will be many people from Kean, many administrators and other faculty members, and a lot of people from outside of Kean and UCC as well. So that should be fun. And you may have heard a little bit of talk about our makerspace, and you'll get a chance to see it. And hopefully you'll get involved in the activities we'll be running there. Wonderful. We ended a little bit early. Thank everybody for coming.
I want to go, so is that coming for me? I don't know.